All right, so the topic we're going to do now is called voltage and current division, okay? Now, what we do with this is that when we have a certain number of resistors that all end up series with one another, and we know that there's a particular voltage that gets applied across that chain of resistors, voltage division says that we can make a fairly easy equation or formula to be able to come up with the voltage drop across any one of those little resistors in that chain. That's what we're trying to do in terms of voltage division. For current division, we are going to limit our scope actually to only two resistors that are in parallel with one another. But in that case, if we know the amount of current that is being driven across two resistors in parallel with one another, and we know the two resistance values, we can use a fairly simple formula to come up with how much current must go in one or the other of the two branches. So that's kind of the big concept of what we want to do with this. I need to emphasize that me giving you this set of equations here doesn't actually add any capability to your ability to analyze circuits, right? There's no circuit that you are now going to be able to approach because of what I derive here that you couldn't already approach with KVL, KCL, and Ohm's law. Okay, so, but what I'm giving you is just sort of giving you a shortcut to find these things in a little bit faster way. So for that reason, I do think it's a good idea to memorize how these work, but it's not absolutely essential that you memorize them, because no matter what, you can always go back to KVL, KCL, and Ohm's law, and you can get the same end. It just might take you a few more steps. Does that make sense? Okay, so let's get into deriving these things. So first of all, let's look at voltage division. Okay, with voltage division, probably the first place to start is imagining, what if I took a circuit like this, where I've got n resistors in series with one another hooked up to a voltage source? What if I wanted to know the amount of current that was flowing in that loop? What would I do? Okay, I could use an equivalent resistance kind of technique, right? I could say I've got this voltage source hooked up into an equivalent resistance, Req. What would that Req value be? Okay, all it's going to be is a sum. This is what we learned, I believe, last time, of whatever an index value is ranging from one end of the range to the other, right? However many of these resistors that you've got. If you number them so kind of sequentially, make like an index value like this, and you just add up each one of those elements. All right, add up the resistance value for each one of those elements. That's going to be the equivalent resistance. Once you do that, how do you come up with the current that the source has to push? This is, I'll just call it I. I is just going to be equal to V over Req, which is just going to be equal to V over the sum, K equal 1 to N, of Rk. That's easy enough, right? Now, because this whole thing is just one series loop, that means that the current that flows through any one of these resistors has to be the same, right? Each one of those currents that flows through any one of those resistors had better be the I value that I just came up with down there. There's no other place for current to go. Okay? Now, what we said we're trying to do is figure out how much voltage are we going to have across any one of the resistors in the chain. Okay? So what that might look like for resistor 2, for instance, we would say this would be VR2, maybe, something like this, plus and minus like that. Right? We're trying to figure out what would that voltage be for that one element. And so instead of doing it for just resistor 2, let me do it generally for resistor K, right? For any of the resistors that are in this chain, I can basically label that with something like VR sub K. Does that make sense? So VRK. Now, how do I get that? The current I just found, I, multiplied by that particular resistance value, which is going to be Rk. right? But if I do a substitution, because I just down here found that I was equal to V over the sum of all these RKs, right? I can change this and say VRK is going to be equal to, let me just keep V out by itself and label this as RK over this sum of K equal 1 to N of RK. This is kind of the fancy math notation to say what we're trying to say. What is that in terms of the concept, though? If I want to know the voltage across any one of these resistors in this series chain, all I need to know is what's the overall voltage I'm applying to the whole chain. That's the V. And then I need to know what is the resistor value itself that I'm trying to find the voltage across. That's RK. And then I need to know what's the total sum of all the resistance values. That's all I need to know, and now I can figure out what the voltage is across any one of those resistors in that chain. Now, I don't know how some of the other maybe sections of this course present this. They may not show you this full version where you can use N resistors in series. Very often when people derive a voltage division type of a formula, they restrict their discussion to just two resistors, okay? If I had that, in this case, let's say I've got a voltage source that I put across two resistors that are in series with one another, and I just label those R1 and R2, and I'm putting V across those. How do I find what my voltage is going to be across either of those two resistors? We call it VR1 and VR2, like this, okay? This equation up here will reduce down to what? VR1 is going to be equal to just V times R1 over R1 plus R2. And for many presentations of voltage division, this is kind of what they do. They just limit the discussion to just 2 instead of having N. All right? What about for R2? The only thing that changes is the numerator of that fraction, right? R1 plus R2 would be down here. Okay? Just to kind of make sure I use this term as well, what you actually see with two resistors that are in series with one another, that is often called a voltage divider circuit. So it makes sense that we're using voltage division technique to figure out how much voltage is across each one of those circuit elements. All right, and that's about it for that one. Any questions on voltage division technique? All right, let's get into current division. And I mentioned a second ago that with current division, our strategy at first here is going to be to just limit the discussion to only two resistors. Okay? Now, if we kind of follow a similar technique that I did last time, what would we want to do first? Perhaps. You might want to come up with an equivalent resistance, right? So let's say I've got this current I that's being driven across the combination of these two resistors in parallel. How would I come up with that equivalent resistance? You could do the reciprocal of the sum of the reciprocals. That's not wrong, but it might actually, because I know what's coming up here in a couple seconds, it might be handier for us to use our other expression that we dealt with last time that was the product of the two resistors over the sum of the two resistors. Okay, so let me just express it that way. Let's say this is just going to be equal to R1, R2 over R1 plus R2. So far, so good. Now, what does that do for me? If I know the current is I, and I know the equivalent resistance is this expression R1, R2 over R1 plus R2, can I figure out voltage? I sure can. Once I figure out that resistance, that voltage comes from basically the voltage across these two nodes, here and here. Those two nodes, if I identify them on the original circuit, would be here and here. So once I come up with this V value for my equivalent resistance, does that still exist when I go back to my original circuit? It does. It didn't go away because I still have the same pair of nodes that didn't leave whenever I made that substitution for REQ. Okay? So I'm going to say that is the V that I have up here, and that is the V that is applied across both of these two resistors. Okay? With me so far? All right, now how would I come up with currents that flow through either one of these resistors? I'm going to label these maybe I1 and I2. Does Ohm's law have anything to say about that? Okay, it's going to be related to the voltage, right? Okay, because voltage over resistance gives you current. All right, so before I do that, let me actually go back to I'm kind of giving you a preview of where we're going. Let me go back to this thing and say, what would that voltage be based on me knowing I and Req? Okay, V is going to be equal to I times Req, R1, R2 over R1 plus R2. Okay, but we just said a second ago that I1 is going to be equal to V over R1. I think that's what we said a second ago, right? Can I substitute this V in there? I sure can. So this ends up giving me that I1 is just equal to I times R1, R2 over R1 plus R2, all this over R1. That means this R1 will cancel that R1. Okay? And that means that I1 is just going to be equal to I times R2 over R1 plus R2. And that form should look kind of similar to what we had for voltage division, with one little difference. Yeah, what you're doing is you're inverting which of the two resistors you put in the numerator. Right? You still have the sum of the two resistors in the denominator, but if you want the current through R1, you have to put the value of R2 in the numerator. Right? So you kind of flip which one of those shows up in that numerator. Okay? So, what if I want I2? What do you think that winds up being? You could show it to yourself, right? But it would be based on V over R2, dot, 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 right? Same kind of principle after that. We would cancel R2s instead of R1s, and we would end up with I times R1 over R1 plus R2. So those are the equations or the relationships we will use for current division, right? Maybe I'll give myself a little bit of room here and say this is I1 and this is I2. And again, they have the same form as the voltage division style, with one difference, and that is, what do you put in the numerator? With voltage division, you put the value itself of the element that you're trying to find, right? And then in the case of current division, right, you put the other one. Cool. Now, this is a question that a lot of people will ask at this point. What happens if you want to extend this out to n resistors? The big answer to that question is there isn't a very clean form of this. Okay? But I want to give you at least some idea of what you could do to figure out what the current is through resistor K. Okay? And let me give myself lots of room to write down here. Okay? What we would do is we can still say it's whatever current was being driven through the combination of all of them. But now, the tricky part is we kind of have to think of collapsing this circuit from being n resistors back down to 2 resistors, where one of the resistors is the one we're trying to investigate, and the other resistor is the equivalent resistance of everything else. Right? So if you think about, dropping it down into that kind of a form, what you could end up saying is that we would have the equivalent resistance of all other resistors than RK. right? So everything else that wasn't RK, you take the equivalent resistance of all of that in parallel and put that in the numerator. Then what you do in the denominator is you take that same value that I just described right there, put that in the denominator plus what? RK. So the reason that this is not usually presented, the idea of doing this for n resistors, is that it's debatable as to whether or not this is actually a shortcut, right? So I'm showing it to you that this is what it would have to look like if you wanted to do current division for n elements. And most people don't do that because it's not actually helpful, right? It doesn't actually make it any more efficient, in most cases, I would say. Let's do an example. The instructions on this example are to find the voltage across and the current flowing through each resistor in the circuit. Okay? And because I'm presenting this example right after I talk about voltage and current division, what do you think I might be inclined to try to use as I solve this problem? Voltage and current division, very likely. Okay? Sometimes, though, it's difficult to figure out how you would start immediately using voltage and current division. As I look on here, what you look for is do I know the voltage across a series chain of resistors, or do I know the current that gets divided up through two parallel paths where I know those resistances? That's what you need for either voltage in the first case or current division in the second case. You need basically a circuit that has something like that embedded into it so you can use the formula. Does this circuit have anything like that? Okay. I would say I know the voltage over here is 12 volts, but it goes through a 105 ohm, and then things split, goes through all this stuff over here, and then it goes down again through the 42 ohm resistor. I don't really just have a plain chain of series resistors, so I can't immediately use my voltage division technique, at least not quite yet. Could I do something, though, that would maybe allow me to do that? What would you suggest? I think what was just suggested is we could come up with what is the equivalent resistance of the stuff circled in yellow over there. Okay? And then when we do that, what we could do is essentially rewrite this circuit where it's 12 volts going through a 105 and through a 42, but then we just replace this effect of these resistors over here with an REQ. Okay? So let me call that REQ. And I'll call this 105 ohms, and this down here 42 ohms. And what is REQ? What I've got there is basically two parallel legs, right? I've got the 63 and the 21 in parallel with the 28. The problem is I do have that 63 and 21 that are in series on that leg, right? Now, if you want to, you can deal with this in two steps. I, a lot of times, will deal with it in one step if it's something this simple. Here's how it would look, right? REQ is just going to be equal to 1 over 28 ohms. That's one of the legs. What would I do for my other term? 1 over 63 ohms plus 21 ohms. Now, you can punch all that in, or you can trust me that I punched it in, and this winds up being just 21 ohms. Okay, but verify me on that. I encourage that. So that's 21 ohms. So now what? I can do voltage division now, right? Because what I want is basically this voltage across REQ. Maybe I'll call it VREQ, right? I want that voltage across that resistor. And now I do have a scenario set up where I can just use straight up voltage division. What would that look like? Okay, it would be 12 volts multiplied by REQ, which would be 21 ohms, over 21 ohms plus 42 ohms plus 105 ohms. Right? That's kind of the more complicated form of the voltage division formula where I've got more than two resistors in series. Right? Okay? Now, again, I encourage you to verify what I do right here, but I got that this value ends up being 1.5 volts. Now go back up and remember, what is it we were trying to find? Voltage across and the current flowing through each resistor in the circuit. Have I done that for anything yet? Okay, I do happen to know the voltage across all of this parallel stuff now, right? The VEQ that I had in the example where I've got it collapsed is the VEQ, VREQ, I should say, across these two terminals up here, or these two nodes, right? So do I know now the voltage across my 28 ohm resistor? I do, okay? And I could just label that if I want to. The 28 ohm resistor has 1.5 volts across that 28 ohm resistor. So that's kind of handy. Can I do anything to get my voltages across my 105 and my 42? Okay, just like I did voltage division right here, that's, the formula ends up being almost exactly the same with just one change, right, to get my voltage across the 105 ohm or across the 42 ohm. What do I have to change if I take this right here? To get the voltage across the 105, let's say, I have to change this numerator to what? 105 ohms. Everything else stays the same because I still have the same sum of resistance around this loop as I did when I calculated V across REQ. Okay, so that ends up giving me, let's see, 7.5. All right, and while I'm at it, why don't I go ahead and get V across the 42 ohm resistor? What's that going to be? 12 volts. Again, we're just going to change the numerator to 42 ohms. In the denominator, we'll still have 21 ohms plus 42 ohms plus 105 ohms. And that ends up giving me, I've got 3 volts there. But you might have been able to see kind of the pattern of the math and be able to figure that out quicker. Why is that? 42 is double 21. It would make sense the voltage across it would be double, right, what it was for the 21. Okay, so we basically got the voltages across the 105, the 28, and the 42. Okay, that sounds pretty good. What do we need to do now? Okay, find some currents, and I'll tell you what I'm going to do here. I'm going to use a technique that allows me to showcase a current division, all right, even though it's not totally necessary for me to do that. Okay, you up for that? Okay, here's what I mean. I could take that circuit that I did up here where I collapsed it down into REQ, and I could collapse it down even more and say I've got a 12 volt source going through just one resistor, like an overall equivalent resistance. What would that resistor have to be? The summation of 42, 21, and 105, right? And so, is that what it is, 68? I believe you. 168. I shouldn't have believed you. No, I'm kidding. I just should listen better. Okay, 168 ohms. And what would the current be in that scenario? 12 volts divided by 168 ohms. And what would that be? 0.0714 amps. Okay? That seems about right. What do I do with that? Get that kind of by itself right there. What he says is that should be good for how much current goes through my 105 and my 42 ohm resistors. I agree with that. Okay? So what that tells me now is that I know I42 is equal to that 0.0714 amps, right? As well as the 105, right? I105 is going to be equal to 0.0714 amps. That's good. Does it tell me how much current goes through the 28 ohm resistor? What do I need to figure that out? Current division would be a good way to do that, right? Because when I found this 0.0714 amps, that is how much current is flowing here. 0.0714 amps is how much flows here. Where does that current have to go? Some of it goes through this leg, and some of it goes through that leg. This is going to be the I-28, right, current through the 28 ohm resistor. Over here, this I'll call I don't even know what to call that one, okay? This would be like 84, right? We'll call that I-84, because that's the current that would go down through the combination of 63 and 21. Okay? What do I do with that? I need this circuit back on my page again, so give me a second. I'm going to copy it. I can do current division. I-28 is going to be equal to 0.0714 amps multiplied by a ratio of resistances, right? What's that ratio going to be? Summation of 63 and 21 is going to be one of the two resistors, and then the other resistor will be the 28. So 63 plus 21 gives me 84 ohms. Because I'm trying to find the current on the 28 ohm resistor, I have to use the opposite of the two resistors in the numerator, and then the sum of the two resistors in the denominator. Okay, and what that ends up giving me is 53.55 milliamps. Or if I want to write it the same way as I was doing on the other ones, 0.05355 amps. I-84 is the current that flows through both the 63 ohm resistor and the 21 ohm resistor. So I get 2 for 1 when I figure that one out, right? That one is just 0.0714 amps multiplied by 28 ohms over 84 ohms plus 28 ohms. And that gives me 17.85 milliamps, or 0.01785 amps. Now, what I just had, I heard a comment from somebody, we didn't really have to do current division again right here. Why not? I could do a subtraction, right? I know that there's 0.0714 amps flowing in here, and I know that 0.05355 amps flows on one leg. If I subtract those two values, I should get 0.01785 amps that must be flowing on the other leg. And I do, right? So there are a couple of options about how you go about finding those. Okay? I think we're actually still missing one thing. What are we missing? Two things. Voltages across the 63 ohm resistor in particular and the 21 ohm resistor in particular. Can I use a voltage division technique for that? You don't have to. You can use Ohm's law. There's actually a bunch of stuff you can use at this point, right? But you could use a voltage division technique because you know that the voltage across the combo of the 63 and the 21 is going to be VREQ. And because you know those two resistance values, you could do like a voltage division and figure out what the voltage was across each one. But now that you know the currents, you could also just do Ohm's law, right? So because I want to complete it out, let me just go ahead and write that down. I'll just do it with numbers right here. Let's say V63 for the 63 ohm resistor is just going to be equal to the current flowing through it, which is 0.01785 amps multiplied by 63 ohms. All right? And when you do that, that ends up being 1.125 volts. What would V21 be? Same thing again, right? 1785 amps, but now multiplied by 21 ohms. And that ends up giving me 0.375 volts. Okay? And I think that takes care of everything that I needed to know. Okay? I could label on this thing if I wanted to each and every one of my currents and voltages across each and every one of my elements. Some people might say, well, you should actually sum, the sum of the voltages across the 63 and the 21 should sum to VREQ, right? Do they? 1.125 volts plus 0.375 volts. Does that give me, what was that voltage up there, 1.5? It does. So everything checks out. Seems like our voltage and current division stuff works just fine. Cool. Any questions? Fantastic.